This is the review of page 358 and page 383 for AP Statistics, covering the first couple chapters of probability. You just had a homework assignment done for me, and I wanted to make sure that I took the time to review said questions so that you had, were able to correct any mistakes that you made along the way. As you can see, I have the online textbook open, and I'm going to be going through each question at a time, going through the various explanations, and I'm also going to have the Elmo camera open as well at various points in order to do some more detailed mathematics written out, just in case it doesn't make sense from the verbal explanation. Okay, click over here. There we go. Good. So you started with number 17. Suppose that 46% of families living in a certain county own a computer and 18% own an HD TV. The addition rule might suggest then that 64% of families own either a computer or an HD TV. What is wrong with that reasoning? Well, yes, 46% plus 18% is 64%. But it is not taking into account the fact that, well, there are some families that could own both a computer and an HD TV, and we simply do not have this information. One could say that, well, the two events in question, it seems that they would not be mutually exclusive, or they would not be disjoint. Thus, the probability of owning both would not be equal to zero, and this rationale of 64% would be flawed. So, yay. Moving over to number 21. Number 21, for high school students graduating in 2015, college admissions to the nation's most selective schools were the most competitive in memory. Harvard accepted about 5.3% of its applicants, Dartmouth about 10%, and Penn about 9.9%. Jorge applied to all three. Assuming that he is a typical applicant, he figures that his chances of getting into both Harvard and Dartmouth must be about 0.53%. Then a series of kind of discussion-ish type questions. Part A, how has he arrived at this calculation? Well, if just thought very briefly about it, I'm sorry, I have the frog in my throat. He just simply multiplied together 0.053 and 0.1 in order to get the 0.53%. I'll show you that in one moment. I'm just looking up one particular thing in my textbook to confirm something. Yeah, of course. Where's my calculator? Flip. Boom. There we go. You can see that pretty well. 0.053 times 0.1 gives you that 0.0053. Make sure you know how you're converting your percentages to decimals and vice versa. So be careful. Part B, what additional assumption is he making? Now, this is something that we talked about in previous classes, and this is something that we actually did talk about a bit today being Thursday the 7th. But there has to be a level of independence. He is assuming that there is independence between getting into Harvard and Dartmouth. Because if the two events A and B are independent, then you could simply multiply the probability of A times the probability of B. If they're not independent, then there is a bit of conditional probability that needs to be done, which you don't have that information. Part C, do you agree with this conclusion? Well, I guess it really depends on what perspective you're coming from. In a perfect world, it should be independent. Getting into one of these exclusive schools, you would assume that none of them are talking to each other, that none of them know what the other is deciding. So, that you would hope that they would be independent. But you have to look at it from a different perspective. These colleges, these higher level Ivy League colleges, use similar criteria. So if his application is not good enough for Harvard, then one could argue that there's a better chance that it's not good enough for Dartmouth or Penn, unfortunately. So they use similar criteria for acceptance. Independence cannot be assumed. Ugh. Number 25. I'm going to turn my page here. Come on. There we go. Now for number 25, I am going to have to write something down because there is some information on the previous page that we do need, and it's from number 23. So let me go back to number 23. Here we go. Car repairs. A consumer organization estimates that over a 1-year period, 17% of cars will need to be repaired once, 7% of cars will need to be repaired twice, and 4% will receive 3 or more. Now, solely based on that information, I guess it would be acceptable to assume that 72% would get no repairs. And you can see that, here we go. You can see that right here. 17%, 7 and 4 were given to you, and 3 or more covered anything beyond that, but 72% would cover the rest of them. So here's the question for number 25. If you own 2 cars, what is the probability that? Well, part A, they want to know neither will need repair. Well, for part A, if neither need repair, then it's, 72% chance and a 72% chance, which should give you 0.5184. I shouldn't really be writing out the full decimal, but whatever. For part B, both will need a repair. Now, in this case, both needing a repair, you don't know how many repairs that is. Could be 1, 2, 3, or more. So in this instance, 17, 7, and 4 add up to 28%, because you could need 1 repair or 2 or 3 or more. And you're looking at, let me read this question one more time. Both will need a repair, meaning the first one will need a repair and the second one will need a repair. And that gives you 0.0784. Part C. Now this is getting a little tricky. At least one will need a repair. At least one will need a repair. Now, you don't know if it's the first one that needs a repair or the second one that needs a repair, and you don't know how many repairs they're actually going to... It's actually a bit simpler than that. 51.8% will need no repairs whatsoever. Thus, the complement of that, 1 minus 0.5184, the complement of that will cover the rest, meaning 1 repair or 2 or 3 or more. If 0.5184 represents neither of them needing a repair, looking at the wording of the question, at least one, meaning 1 or more repairs, or at least one, meaning 1 or more cars, I should say, should be the rest of that probability. It's a basic complement type problem, because either at least one of them will need a repair, or none of them will need a repair. Together, that's complete 100%. Number 29. Independence. Now, this is more of a verbal kind of question. As discussed in this chapter, sometimes the independence assumption is reasonable, but other times it is not. Consider the following situations. Comment on whether you think it's safe to assume independence. A pollster asked every 20th person exiting a movie if they liked the movie or not. I mean, you know better than anyone. You go to a movie, you could like it, you might not like it. It really depends on what the movie is. Just because you see a movie doesn't guarantee that you're going to like it. And if you're asking every 20th person, meaning this is systematic sampling, then yes, you can argue that this is random, and thus the responses would be independent from each other. You can assume independence there. However, for part B, now the pollster's asking people exiting a movie if they liked it or not, but he's asking people in groups. See, unfortunately, if you're in a group of people, You may not want to let your true opinion be known, and your opinion may be based on other people in your party that you're going to the movies with. So unfortunately, with Part B, you cannot assume independence. In fact, it really comes down to random selection. Asking a group is not really random, considering that people within the group, their opinions may be affected by other people. Part C, the amount of rainfall in a given city over the course of 10 days. Not independent. Which city is it? Are you picking a city that gets mostly rain throughout the year or mostly no rain throughout the year? I mean, it's not really randomly selected. I mean, it could be a randomly selected city, but because you're only doing one city over the course of 10 days, is it the rainy season? Is it not the rainy season? Who knows? Not independent. But for Part D, you're picking 20 randomly chosen cities on a given day of the year. Now, I don't know if this is across the United States or across the world. I want to assume the world because there's a little globe in the corner right there. But if you're picking it across the globe, then you could get a mix of all types of seasons because we're in the winter up here. It's the summer down in the southern hemisphere. Who knows? But yeah, you could assume independence there. Number 34. Now, number 34 bleeds into number 36. So I actually am going to write down this little table to make it, no pun intended, easier for me to remember some of these numbers. So that should be 501, 802, 682, 20, and it adds up to 2005. So I have those numbers right there to reference so that I don't have to keep flipping back pages. If we select a respondent at random, what is the probability that they would have responded harder? Well, clearly that's 682 out of 2005. 682 out of 2005 should be approximately 34%, 4.34. Part B, what is the probability that the person responded the same or easier? You can't respond both. So these two events are mutually exclusive. Same or easier, that would be 501 plus 802 divided by 2005. The answer should be about 65%. Now, as I said, number 36 does have a similar situation going on here because it's Fathers Revisited. Consider again the results of the poll about fathering discussed in exercise 34, but now they're selecting two people at random. Okay. What is the probability that both think being a father is easier today? Well, being a father being easier today, 501 out of 2005 chose that. But since you're selecting two, it would be the first one answering that and the second one answering that. So I'm just going to square it. About 6.2%, 0.062. Part B, what is the probability that neither thinks being a father is easier? Well, if they did not answer easier, then it's got to be the rest of them. It's got to be the 802, the 682, and the 20. Neither think it's easier. Well, it's 1504 out of the 2005. So that's the first one answering a response other than easier, and the second one answering a response that wasn't easier. It's about 0.563 is what it rounds to. Then we come to part C. What is the probability that the first person thinks being a father is easier and the second one doesn't? Well, the first one believing it's easier and the second one, what was the wording? And the second one doesn't. That's 1504 out of 2005. That's about 18.7%. Part D. What assumption did you make in computing these probabilities? Well, in order to just multiply them straight up, these responses had to be independent of each other. And as long as that's true, I can just multiply the probability of A times the probability of B. Explain why you think that assumption is reasonable. Well, let me go back to number 34. A Pew Research poll. Now it doesn't, it says it down here. If we select a respondent at random, well, okay, I guess that can be assumed. But because it's a Pew Research poll, you can assume that these numbers were gathered from a random sample. It's not that this random is saying that it's a random sample. The fact that it was from the Pew Research poll means that you assume, yeah, they got a correctly collected sample of people. Go back to that. But yeah, let's go to page 383. Number 12. Oh, I just passed it. Now for this problem, I am going to have to draw something. So let me get a new piece of paper. Because drawing this picture for number 12 is going to be incredibly helpful. They say 73% of Americans have a laptop or a desktop. Or not or, but a laptop desktop. Some kind of like computer. I'm just going to put comp. And then 45% have a tablet. And 36% have both. Well, this is what I've drawn so far. Now, being that 73% of Americans own a computer, that must mean that this circle is 0.37, because together those two numbers make 73%, which is the percent of people who own a computer, some kind of computing thing, not a tablet. But then they say that 45% own a tablet, and because of that, this circle is 0.09, because 36 and 9 make 45%. Now, if you add up all three of those numbers, you get 82%, which implies that 18% don't fit into either category. This Venn diagram is going to be incredibly helpful for answering the questions. Let's go to it. Number 12. What is the probability that they own a tablet but not a desktop laptop? That's the 9%. That's the answer to part A, 0.09. Or you could just do 45% minus 36%. But I like the Venn diagram better. Part B, they have either a tablet or a desktop laptop. You could do this in one of two ways. Using the information that they give you without the Venn diagram, you could be like, okay, 73 plus 45 minus 36, because that would be the probability of A plus the probability of B minus the probability of both. And that would give you 82%. Or you could just add up these three numbers, and that would give you 82%. Having one or the other, meaning they could have both, but it's 82%. Part C, they have neither. Well, we just figured that out. Or you could do the complement of part B. Part B was they have one or the other. Part C is they have neither. They're complementary statements. All right, let's look at number 15. Click. Number 15 gives you this giant table. Oh my goodness. Marketing research team, GfK, Custom Research North America, conducts a yearly survey on consumer attitudes worldwide, whatever. They want to know where you're from and what was your education level. Got it. If we select somebody at random, what is the probability that they're from the US? Well, put my calculator back into play. There are 1557 people from the US in the survey. And 7690, according to this, 7690 that answered the survey. So yeah, 0.202. Part B. What is the probability that the person completed his or her education before college, meaning that they stopped their education before college? Now, you can't include no answer. You don't know what they did, but you cannot include no answer. So you're going to be using the 4195 and the 1161. That's 5656. Did I type that right? 4195. Let's try that again. 5356. That sounds better. Divided by 7690 gives you that 0.696. And you can't include no answer. That's some high school or primary or less. Part C. What is the probability that the person's from France or did some postgraduate study? Okay. 69 did both, postgraduate and France. All right, we'll figure this junk out. 1539, watch this. 1539 were from France. 379 did postgraduate, and 69 did both. That gives me 1849. That would be the probability of A plus the probability of B minus the probability of both. Divided by 7690 gives me 0.240, which is my answer, 24%. Part D. What is the probability that the person's from France and finished only primary school or less? Now, primary school or less, right here, 309 people. Primary school or less and from France. I'm just going to divide that by 7690. About 4%. That's all the problem really came down to. It's just properly identifying things within the problem. The hardest part about problems like this is just figuring out what the heck the problem's even asking. Proper interpretation. Let's look at number 25. Cards, 25 and 26 actually. You are dealt 3 cards, one at a time. Find the probability of each of the following. You need to draw a heart, and you do so on the 3rd try. Now, just for the record, there are 13 hearts in the deck. There are 39 cards that are not. If you get the heart on the 3rd try, it implies that you did not get the heart on the first 2 tries. So the way that this calculation should really be done, let me zoom in right here. There we go. The way that this calculation really should be done, there's your first card, not being a heart. There's your second card not being a heart. Notice that there's one less in the top and bottom. Now there's still 13 hearts in the deck. And your third card being a heart, there's only 50 cards to choose from when that happens. This is the answer to part A. 0.145. Now it gets slightly more complicated from here. Part B. Your cards are all red. That is diamond or hearts. There are 26 cards that are red. Let me just bring this back. I don't feel like retyping this. That's the proper calculation for part B. The first card being red, the second card being red, you have one less of each, and the third card being red, you have one less of each. 0.118. Part C. you get no spades. Now keep in mind there are 13 spades. There are 39 cards that are not spades. So 39 cards that are not spades. You get no spades. That looks about right. You get no spades. 39 cards are not spades. Once you pick one, you have 38 left. Once you pick one, you have 37 left. That is the answer to part C. Part D, you have at least one ace. Now, having at least one ace is a little difficult because you could have 1 or 2 or 3, and there's a complicated order that can happen in. So instead, the smarter way of going about part D is utilizing the complement. The complement of having at least one ace is calculating no aces. If you're going to calculate no aces, that is the probability of having no aces. But this problem says, well, what's the probability of having at least one? Meaning the complement, which is 0.217. Card problem? I love card problems. Number 26. You pick 3 cards at random. What is the probability that you will get no aces? Wait a minute. Didn't we just do that? It was that thing right there. That's the probability of getting no aces. Well, that one's done. 0.783. Part B. You get all hearts, meaning the first one was a heart, the second one was a heart, and the third one was a heart. You have to account for the fact that you're not putting them back. 0.013. Part C. You want to draw red. You do so on the 3rd try. Okay. Well, that means that you didn't do it on the 1st try because there are 26 black cards. You didn't do it on the 2nd try, but you did do it on the 3rd try, which means it goes back up to 26 because there are 26 black cards, and then there's only 25 left, and then there are 26 red cards. That 3rd try is the one that you do it on. 0.127. Have at least one diamond, similar to the ace problem in number 25. Instead of calculating at least one diamond, calculate no diamonds first. Calculating no diamonds first and then doing 1 minus to get the complement. 0.586. Again, the idea of having at least one diamond means you have 1 or 2 or 3 or, well, there's 3 cards really, 0, 1, 2, or 3 are the only possibilities. Calculate the chance of getting 0 and then find the complement. That's the easiest way to go about it. Number 33. If you draw cards at random from a well-shuffled deck, they're looking for whether or not getting an ace is independent of the suit. Let me show you something here. The probability of getting an ace is 4 out of 52, which is approximately 0.077. But if you're looking for independence, the definition that I gave you for 2 events being independent is you have to look at the probability of B versus the probability of B given A. So let's look at the probability of ace given a suit. I'm just going to pick a suit. Let's pick spades. Given that you were only looking at the spades, given that the spades are the only cards that you are choosing from, you are only choosing from 13 cards. And of those 13 cards, only one of them is an ace. 1 divided by 13, if you did the calculation, lo and behold, is the same number. This is evidence to suggest that the two events, selecting an ace and selecting a suit, are independent of each other. This is evidence to suggest that. All right. And finally, number 53. Let's go over to number 53 because I'm going to have to draw a tree. Number 53. Dan's Diner employs 3 dishwashers. Now, as I'm reading this, I'm going to be drawing at the same time, so please forgive me with my pauses here. Al, Betty, and Chuck. Al washes 40% of the dishes, and he breaks about 1% of them. I'm going to abbreviate break and no for each of them, just so you know. I'm going to abbreviate break. Well, the word no is just no, whatever, don't care. But Al breaks 1% of those that he handles. And I'll show you this tree in a moment. Betty and Chuck wash 30% each. Betty also breaks about 1%. And poor Chuck, he breaks about 3% of them. Let me flip back over here and zoom back out. There we go. Al, Betty, and Chuck, 40%, 30%, 30%. Al breaks 1% of them. Betty breaks 1% of them. And Chuck breaks 3% of them. And when they say of them, they're referring to of the ones that they wash. And now for the question. The question is, you go to Dan's for supper one night and you hear a dish break in the sink. Given that it breaks, given that you hear that one of those dishes break, what is the probability that it was Chuck on the job? What they're really asking for, if I could break this down, they are looking for the probability that it was Chuck, given that you heard a break. Given that you heard a break, what is the probability that the break was from Chuck? Well, as we've done in the past, I need the probability of both of them, Chuck and break, divided by the probability of break. If you follow the tree along Chuck's branches to break, 0.3 times 0.03 is 0.009. That is the probability of it being both Chuck and the dish breaking. But I have to divide it by the probability of the thing breaking. Well, if it breaks, it could have been Chuck. It also could have been Betty. It also could have been Al. In order to find the probability of it breaking, we're going to have to do the calculations for each of the breaking branches. If you multiply along Al's branches, come on, you get 0.004. If you multiply along Betty's branches, you get 0.003. If you add up those three numbers, because it could have been Al or Betty or Chuck that caused the break, if you add up all three of them, you get 0.016. Given that it broke, what are the chances that it was Chuck? 0.009 divided by 0.016 give you 0.5625, or 56.3%. If you have any questions, please make sure that you email me, and please pay attention to Google Classroom. as we continue with these lessons. Thank you.